Let's now proceed to finding the stiffness matrix of a single spring. So far we discretized the spring into one element shown with the circle and two nodes, node 1 and node 2 here. And then we drew the free body diagrams with F1x1, which I said again. Let me just review what we learned. That F1x1 means force at node 1 of element 1 and x direction in local coordinate system. And the local coordinate system means in the along the length of the spring. And then again, as I said previously, F and D, which is force and displacement for all the nodes, are in the positive x direction. If you remember, we assigned this as our local coordinate system. But when we drew the free body diagram of the nodes, we said that the F1x and F2x for the nodes were in the opposite directions, and the external forces were applied to the nodes as they would be applied to the actual spring or element. So here for node 1 we had the reaction in the negative x direction, and at node 2 the force was applied in the positive x direction. And having applied equilibrium to nodes, we found that the F1x1 is equal to minus F and F2x1 is equal to F. Now for a spring, we know that F is equal to K delta, or as I also said previously, F is equal to Kx. They're basically the same thing. F is the force, K is the displacement, delta or X is the deformation or displacement, or K is the stiffness of the spring. So from the displacement function, we can find delta. Delta is equal to U of L minus U of 0. Basically, the difference in the displacements of the spring at the two ends of it. So this is one end of the spring and this is the other end of the spring. If we subtract the two displacements from the displacement function, we find the displacement of the spring delta, which could be used in this equation, F equals K delta, or similarly F equals Kx. So having known that, and having known that we have two nodes and for each node we have force and we have displacement, we can form the nodal force vector. So this is the nodal force vector, and this is the nodal displacement vector. Let me just write that. So the nodal force vector has the two forces F1x1 and F2x1, and the nodal displacement vector has the two displacements D1x1 and D2x1, basically the forces and the displacements at each node. Now if we have that equation F equals K delta, we can also rewrite it as F equals to K D2x1 minus D1x1, which again is delta in here, and K is the stiffness of the spring. So we can replace F with either F1x1 or F2x1, but we have to remember that F1x1 was negative F, so we apply that negative sign there. So F1x1 for element 1 is equal to K delta KD2x1 minus D1x1. So if we bring this negative sign from the left hand side to the right hand side and rearrange it, F1x1 becomes K times D1x1 minus D2x1. Similarly, F2x1, so force at node 2 in x direction for element 1 in the local coordinate system, is equal to stiffness times D2x1 minus D1x1. So now that we have this in here, you can pay attention that the signs between these two parentheses is different. D1x1 minus D2x1, and here is D2x1 minus D1x1. So now if I rearrange all of these equations into a vector or a matrix form, I can write F1x1 and F2x1 and here I have d1x1 and d2x1. So how do I find these k's and minus k's? Well, if I assume, let me change the color of the ink here to green. What I want to have from this spring or from this matrix is that f1x1 should be, if I say this is k11 and this is k12, k11 times d1x1 plus k12 d1 or d2x1, I'll write it that way, should be equal to k d1x1 minus d2x1. And that's how I find k11 and k12, because this one should be minus k and this one should be plus k to make this happen. And then similarly for the f2x1, I can say f2x1 is equal to k21 times d1x plus k22 times d2x, and then look at the signs in this equation and find that k times d2x1, which is here, and minus k times d1x1 there, make up this stiffness matrix. So we found that the matrix formation or notation for the forces and displacements of a spring is like this. Here we have the nodal force vectors, and here we have the nodal displacements, and here is the stiffness matrix, which we show with this. And again, the hat on top of this k means that we are in the local coordinate system, and the displacement of or the stiffness of the or stiffness matrix would be this 2x2 equation or matrix. This is a 2x2 matrix. One thing to notice in here is that it always is 2x2 or a square matrix. It depends on the number of nodes and number of degrees of freedom per node. So basically the rule of thumb is, let me write that with a different color. The order of k, whether it's local or global stiffness matrix, is equal to the number of nodes times the number of degrees of freedom per node. So we have two nodes here. If I go back to the free body diagram, we have node 1 and node 2, and we only have 1 degree of freedom per node. So we have d1x and d2x, which is basically displacement. So going back here, I have two nodes and I have 1 degree of freedom per node, which means 2 by 1 is equal to 2. That's why I have a 2x2 matrix there. Again, this is a local stiffness matrix because it is in the local coordinate system of only one element. So because we only had one element here, we can remove the hat signs and make up and write this as its global or total stiffness matrix. They're both the same right now. So because it doesn't have the hat sign, they are in global coordinate system. And also because we only had one element and all the nodes are included in this matrix, this could also be called the total stiffness matrix. But we'll cover these notations throughout the course, so don't worry about it right now. I'm just telling you what these hats and not hats mean. So we have F1x and F2x without the elements or element numbers there. And we have k minus k minus kk, d1x and d2x. That this is the system of equations that can be used to solve the spring that we had. So the boundary condition that we have for this problem is like this. d1x is equal to 0 because it's the fixed end, and d2 or f2x is equal to f, which is the external force applied to the spring. So we don't know this f, and we don't know this d2x. However, our knowns are, and I want to show them with green, the ones that we know is that d1x is 0. That's our known boundary condition. And f2x is equal to f, which is the known external force. Now I can use those to solve these equations. So I can say f is equal to minus k. So f is equal to minus k times 0 plus k times d2x. So minus k times 0 plus k times d2x. This one will be 0. And k times d2x becomes equals to f. As a result, d2x is equal to f over k, which is basically the displacement of the end of the spring. Now f1x, which is another thing that we don't know, is going to be equal to k times 0 minus k times d2x. Now we know. So f1x is equal to k times 0, which is again equal to 0, minus k times d2x, which means minus k times, if you put that here, f over k is equal to minus f, as we expected. So the force at the fixed end of the spring is equal to the same force, or the reaction force would be equal to the external force, but in the opposite direction.